We are live now. Link. Okay. Okay. So these are the main topics we have to cover in week 1 and 2. So it is. We will start. You should understand first of all what is this jointly distributed. So if I talk about two random variables or multiple random variables, what is this joint probability mass function is that you have to know. And after that, we will see the marginal probability mass function, conditional PMFs, and then later we will see the independence, which is independent random variables. So when will I say x and y are two random variables, x and y are independent to each other, and when they are not independent, that things. And then the most important thing, maybe not for the exam point of view, but later throughout the course, you should know what is this, what are these IIDs means. So these are in short called as IIDs. So it is independent identically
I
distributed. Uh, okay, before that, I request everyone to be on mute. I'll give chance all of you. Those who have doubts, I will give chance to you guys. But while we are in this revision session, I hope I request everyone to be on mute. Thanks. So then finally we will see a function of a random variable and multiple. It's not random variable. It's we will see functions of random variables. So there can be functions of two random variables. We will see all these things. Okay, let us start by I want to go quickly about this joint PMF, marginal PMF, conditional PMF, because by now you should be knowing what are they. But anyway, I'll just revise it briefly, and we will look at the problems later on. So joint probability mass function, or in short, we will call it as joint PMF. So what is this joint PMF is? If I have two random variables x and y, let's say x and y are discrete as of now. So these are two discrete random variables, okay, and they are defined on some probability space. And added to that, each of them has some range. Okay. So let's say tx is the range of the random variable x, and ty be the range of random variable y. Now this joint PMF, so again it's a probability mass function. So as it is probability mass function, it should be denoted, or it will have an input, output, and all. It's like a function. So this joint PMF is denoted like this, fxy. So this is the function that represents the joint PMF. So this is defined from Tx cross Ty. So when we say Tx cross Ty, it's a two-dimensional input. So two inputs will go inside. So it's like one input from Tx and another input from Ty. So this is how the inputs for this function are. So it's like a two variable input. Two variables will go as an input, and it will map to some number between 0 to 1. Okay. This is how the function, the joint PMF function is defined. So this is the domain of the function, and this is the codomain of the function. And how it is defined is fxy of x comma y, or let me use the professor's notations, t1, t2. So this t1 is coming from the range of tx. This t2 is coming from the range of ty. So the input for this function is ordered pair t1 comma t2. So this is the input. So when this goes as an input, the output is actually probability that x taking value t1 and at the same time y taking value t2. So it's the collective probability we are looking at. The probability that x is equals to t1 at the same time y takes t2. And this holds for all t1 belongs to tx and t2 belongs to t1. Okay. So this is the joint PMF. So joint PMF is like you are combining the PMFs of X and Y's and looking the PMF, jointly looking the PMF. So that is what joint PMF is. And this has some properties also. This usually represented in a table form, where X and Y will be like this. So this will be Tx and this will be Ty, and each of the entries of this table will be the probabilities, corresponding probabilities. So this is how the joint PMF table will be. So given a function, you can create a joint PMF table. Given a joint PMF table, you can understand the jointly distribution of X and Y. And this particular joint PMF has few properties, or this table will have few properties. So I will write it down, properties of joint PMF table. So the first one is each entry, whatever the entry in the table, so each entry in the table is between 0 and 1. Okay. So each entry, so whatever the entry, this is the first row, first column entry, this is second row, second column entry. So every entry in the table must be in between 0 to 1, inclusive. So either it can be 0 or 1 also. And the second property is, if I look at the sum of all the entries in the table, that should be equal to 1. Okay. So the second property states that, so here in this particular thing we have 12 entries. So if I add all the 12 entry values, I should be getting 1. So then that can represent a joint PMF table. These are the two important properties, you can say. Okay. So that is joint PMF. So we'll see an example. So let me complete marginal PMF and conditional PMF also. Then we will see an example, very good example, contextual based example, which we are going to solve after doing this marginal and conditional also. So let me talk about marginal PMF too. So after looking at joint PMF and the table of joint PMF, we can actually compute the marginal PMF. So the marginal PMFs are nothing but, you can treat it as like an individual PMF. If I don't want to include the other random variable, what is the probability mass function of X? What is the probability mass function of Y? So if you know the joint distribution between X and Y, then you can compute the separate probability mass functions of X and separate probability mass functions of Y. So these separate probability mass functions are called marginal PMFs. Okay. So if you have X and Y, you know that it is jointly distributed. Jointly distributed again. So we are still in the discrete case. Jointly distributed discrete random variable. And let's say with the joint PMF as, with some joint PMF fx, with some joint PMF fxy. Okay. So we are looking at the individual PMF. So marginal PMFs, or you can treat it as individual. So this marginal PMF or individual PMFs are defined as fx of x. So if I am talking about fx, this is t1, let me say t1. So this is same as probability that x takes t1, and this I can compute using the joint PMF table. From that joint PMF table, what I do is I will add up all the joint distribution values of t1 comma t2, where this t2 comes from the range of 5. So what I am doing here is, so let me take that example again. I'm not filling the values. Let us say 0, 1, 2, 3, and y also takes 0, 1, 2, 3, 1, 2. So now let's say use some random stuff. 1 by 16, 1 by 16, 1 by 8, 1 by 16, 1 by 8, okay. And we are done with 1 by 16. So now it is like 1 by 8, 1 by 8, 1 by half. So we are done with half, some zeros. 1 by 4, 1 by 4, 0, 0. So let it be like this. So now what this states is, so I have x takes value 0, 1, 2, 3, y takes value 0, 1, 2, but I know the joint distribution. So this 1 by 16 is basically representing, this 1 by 16 is probability that x is equals to 0 and y is equals to 0. So this is the joint probabilities. So each one of the entries is a joint probabilities. If I wanted to compute the marginal probabilities, so something like probability that x is equals to 0 or probability that x is equals to 1. So this t1 is either 0, 1, 2, 3. So if I generally look at t1, that is probability that x is equals to t1, what I have to do is, if this is t1, then I have to add up all the values in this particular column. Okay, so that is like, for example, if I wanted fx of 1, if I want to look at the probability that x is equals to 1, what I have to do is I have to sum up all the joint probabilities by keeping x constant and adding up all the values, all the unwanted y values. So that will become like this, fxy of this 1 will stay constant, and throughout the range I will sum up all the joint probabilities. So t2 will vary now. T2 belongs to the range of ty, and the range of ty is 0, 1, and 2. So that means I have to add 0, and then I have to add 1 comma 1 plus f of xy 1 comma 2. So this will stay constant, but I have to add up all the joint probabilities by varying the unwanted y. So f of xy 1 comma 0 is this, f of xy 1 comma 1 is this, f of xy 1 comma 2 is this. So from the table, what you have to do is, instead of these formulas and all, if I want the probability that x is equals to 1, you go to the column 1 and add up all the table probabilities. So it will be like 1 by 16 plus 1 by 4, it will be 5 by 16.
Sir, can I ask a doubt here?
Yeah.
The reason why we get the marginal PMF, is it because the when we fix x is equal to 1, the rest of the values of y, the probability for the rest of the values of y add ups to 1, and we only are left with the value of x is equal to 1?
Something
Okay.
like that. Something like that.
Okay.
So you have to see, it's like when I am looking for probability that x is equals to 1, you have to see the joint distribution, and y can be anything. Y can be 0, y can be 1, y can be 2. We are not worrying about y. The only worry is what is the probability that x is 1. So when y adds up, it will vanish off, and we will be remained with only x probabilities.
Got it, sir.
Okay. Yeah. So similarly, if my t1 is something like 3, so then you have to go to the column 3, this particular column, and add up all the values and write it below. So it will be again 5 by 16. So what it tells is this 5 by 16 and this 5 by 16, these are the probability that x takes value 1 and x takes value 3. Similarly, if I add this, yeah, any doubt?
Yes, sir. I have a doubt that here we are having table, right? But in most of the cases and most of the questions, or in real life scenarios also, we will not be able to construct these large tables. So in that case, how can we say that these values will only accumulate to the value, means say x is equal to 1 or 2, 3? So how will we approach in that way when we can't make the table?
When you can't make the table, you just have to go with the formulas. If you are unable to make the tables, then you have to add up all the range values of y by fixing x constant. So you have to use the formula.
Yeah, because
So,
actually I was solving today's practice assignment one, and I felt like that because I was not able to make for some of the questions as tables, which I was not able to make.
can you give that example? We will try to solve it. Okay.
Okay, sir. I will share. Just give me.
Yeah. So meanwhile, let me discuss this. Okay.
Yes.
Yeah. Okay. So this is what marginal PMF of x. So when I want marginal PMF of y, so we have to look for other random variable also. So that is also like fy of, if I want, so for the t2, it represents probability that y takes value t2. So now I want y. So add up all the unwanted values. So unwanted random variable values, so which is x values. So now I have to take t1 to be varying throughout the range of x, and I have to add up the joint probabilities t1 comma t2. So in the table, what you have to do is, when you are in the table, you know you have the table. So if you want the probability that y is equals to 0, go to that row and add up all the values in that row. So if you add up all the values in that row, you will be getting 5 by 16. Okay. So this is the marginal of y. So this is the denotion of marginal of y, just like the PMF of y. So this is marginal of x. So this will be 3 by 16 and this will be 3 by 16. Okay. Similarly, so this is the marginal distribution of x, or the individual PMF of x. So now you can see it will satisfy all the probability mass function properties. If you add up, you will get 1. So each of the value in the range, it has some non-zero probability, 3 by 16, 5 by 16, 3 by 16 and 5 by 16. So you can write down the distribution of x. So the distribution of x will be x, and probability that x is equals to x. This will be 0, 1, 2, 3, 3 by 16, 5 by 16, 3 by 16 and 5 by 16. So this is the PMF of x, individual PMF of x, which we got from the joint PMF. So if you know the joint PMF, you can construct the marginal PMF or the individual PMF separately. Similarly, you can do this also. This will be 3 by 8.
Yeah,
And
3 by 8 and 5 by 16.
5 by 16.
5 by 16.
Again, you can write down the table of y. Y is equals to small y, and probability that y is equals to small y. So y takes value 0, 1, 2, and with corresponding probabilities 5 by 16, 3 by 8,
3
and
by
5 by
8.
16. So this is the individual PMF of y, and this is the individual PMF of y. So we use the term called marginal PMF. So this is the marginal PMF of y, and this is the marginal PMF.
Sir, given marginal PMF, can we find joint PMF?
So I'm coming there. So that is the next point I wanted to mention. So given joint PMF, we can construct, or we can solve for construct. I can say construct. We can construct the marginal PMFs, and this is true. But will the vice versa work? So given joint, given marginal, my question is, can we construct the joint?
So not necessarily.
No, sir.
So the answer is no. So this is
Only
no.
when independent we can.
Only independent you can construct, or else no. I didn't discuss independent, so I can give you a simple example where it fails. So just take two values, two possible values, 0, 1, 0, 1. Okay. So if you know the marginals, so for suppose let us say I know the marginals. I know the marginals to be something like 1 by 4, 3 by 4. This is 1 by 3, 2 by 3. So this is the marginal distribution of y. This is the marginal distribution of x. So can I say what value will be coming here and what value will it take here? So I can give you two different possibilities now. So I can give 1 by 8 here. Okay. So once I give 1 by 8 there, this should be 1 by 8, and this is 5 by 24. This will be, once it is 5 by 24, 6, 18, 13 by 24. Let's check whether this is correct or not. 3, 16 by 24, 2 by 3. Okay. So this is correct. So this is one possibility, and the other possibility, I can simply take 1 by 12, 1 by 4, 1 by 6, and 1 by 5. So even this will also give me the same marginal xy 0, 1, 0, 1. So if I add up these two, I will be getting 1 by 4, right? 2 by 2, 3 by 12, 1 by 4. So this is 1 by 4, 3 by 4, 1 by 3, 2 by 3. So you can see here, you for the same marginals, you have two different joint PMFs. Okay. So that is why we cannot construct an unique joint PMF. So maybe the joint PMF which you have constructed will not be unique, may not be unique. So that's there. This is one property you should be knowing, I can say. So given the joint PMF, we can construct the marginals, but given the marginals only, we cannot construct the joint PMF, or we cannot uniquely define the joint PMF. Okay. So you can construct the joint PMF, but it will not be unique. Maybe I will add uniqueness. Struct unique. Right. So there are multiple joint PMFs possible for a particular margin. Okay. So that is about marginal. Marginal PMF is nothing new. It's just the individual PMFs we are computing from the joint. Okay. So that is marginal. Let me also discuss conditional PMF. So basically, again, this is like the same thing. So I have given, I will be given x and y are jointly distributed. Distributed random variables with PMFs with the joint PMF fx1. Okay, this is there. Now, what this conditional PMF is? So I will be conditioning on one random variable. Conditioning on one random variable means, so I will be giving you that this particular random variable x has taken, I am restricting my random variable x. So it has already done. So that experiment done, and the random variable outcome we have seen. So depending upon the condition of the outcome of one random variable, how is the distribution of the other random variable? So that is the conditional distribution. So looking at the distribution of, I will write it in layman terms. So this is conditional distribution means looking at the distribution of y. So we are looking at the distribution of y. So the condition given that x is taking some t1. So this is what the conditional distribution is. So we will represent the denotation of this conditional distribution will be somewhat like this: Fy. So this long bar is like given x is equals to t1 of the input is the whatever the value that is in the range of y. So some t2. So we are interested to look at the distribution of y given given that random variable x has the other random variable x has taken some value. So this is actually probability that y taking value t2 given that x is taking value t1. So this is a conditional distribution, conditional probability now. So conditional probability can be written as like this: y is equals to t2 intersection x is equals to t1 divided by probability that x is equals to t1. Okay. So the top one you can see that is the joint PMF. So this can be written as y is equals to t2 at the same time x is taking value t1. So it's the joint distribution divided by the below one denominator is the marginal distribution, probability that x is equals to t1. So we will be concluding with this main property or main note, you can say, which gives us, maybe you can say it as a theorem also, which gives the connection between the conditional PMF, the joint PMF and the marginal PMF. So that is the joint PMF can be written as product of marginal into the conditional. Conditional PMF. Okay, what it says is f of fxy, whatever it is there, this can be written as fx of x times fy given x is equals to x. Okay, so if you condition on if you are conditioning on x, if you condition on y, it can be written as fy of y times fx given y is equals to y. So this can also be, it can also be written like this. So this is important formula, you can say. This connection between joint, marginal and conditional is very much important, and it will help us to solve many problems. Not only problems, sometimes where it helps is if you are unable to get the joint PMF, and sometimes it will be easier to compute the conditional and marginal and take the product and get the joint. Okay, so it will help you like that. So this connection is very important, and on noting that, we will look at the problem now.
So, quick question. So we only need to know one of the two, the three, any of the two, right, to find the third one. Okay.
So see, the another point is, if you know the joint PMF, you can compute the marginal. So once you can compute the marginal, you can compute the conditional. So joint PMF is like head of PMFs. So if you know just joint PMF, then you can compute marginal as well as conditional.
Got it.
But the other things, like if you know only the marginal, then it is very difficult for us to compute conditional and joint. Same goes with conditional also. If you just know the conditional PMF, you cannot compute marginal and joint. So only the joint PMF has that power, and using the joint PMF we can compute the rest of the thing. And if we know marginal and conditional, then we can compute joint. Okay, so that is there. And now let us look at an example. So this is the example I have done it in previous term also, and the same example I wanted to do now because I felt this gives more clarity on joint, marginal and conditional PMF. So the question statement is like this: a statistics course instructor classifies his students according to their grades and their age groups. Okay. So below table gives the proportion of students falling into that particular categories. So what I changed is I have given the table, but I have put a variable inside it, which can be computed. Okay. So I have given the table, and the table has some 9 entries. Out of the 9 entries, I have given the 8 entry values, but the center entry value is I have given it as k. Okay. What I want first of all is maybe the course instructor has lost that value and he wanted to compute that fraction. Okay, proportion of students who are falling, who got grade A and are in between the age of 20 to 60. So can I compute that k?
Yes, sir. It's
So that
0.2.
Yes, sir.
And what is the value?
Sir, 0.2.
Okay, so someone is saying 0.2. So is this correct? Other people?
Yes, sir.
Yeah. So what you have to do, if a given table, in the given table, if there is an unknown constant, so you can use the properties of the joint PMF table. So one property states that if you add up all the entries, that should be equal to 1. So use that property and get the value of k. So the value of k now is, okay, I will remove now k and I will put 0.20 here. Okay. So now that I have the joint PMF table, the questions I can think of is, what is the probability that he or she, so a student is randomly selected. Okay. So from this, a student is randomly selected. What is the probability that he or she got an A grade? So first of all, how do I convert this into the mathematical denotation? So what are they asking basically? The first question, just tell me that first. So
Marginal of A.
Summation of column A.
marginal of A. Correct. So what is the probability that he or she got an A grade is nothing but, so if you see grades as a random variable and age as a random variable, grades can be S, A, B. Out of that, we wanted what is the probability that it is A. So that means grades taking value A. So that means we are asking about the marginal distribution of the grades, and out of that we wanted the probability that the grade is equal to A. So this ultimately turns out to compute probability that grades taking, that means marginal of A. So what will be the value?
0.4.
0.40.
0.40. So you have to add 0.15 plus 0.20 plus 0.05. That will give us 0.40. Easy as of now. So this is marginal PM. So the next question is, if the student selected, whatever the student we have selected, if the student selected is from 20 to 60 age group, then find the probability that he or she got an S grade.
So 0.5.
Now tell me, what kind of problem is this? So which concept is this problem related to?
Conditional.
Conditional. Correct. So this is the condition given to us. The condition is he or she is from 20 to 60 age group, and you have to find the probability that he or she got an S grade. So what this means is you have to identify, compute the probability that grades, the random variable grades is S, given that the age is from 20 to 60. 20 to 60. Okay. So this is what you have to compute. For this, you need the joint divided by the marginal. Correct. So what is the value?
0.05
divided by
Correct.
0.1.
So 0.05 divided by, so this joint divided by the marginal is, I have to add up all the rows. 0.50. Correct. So 0.05 by 0.50. So this will be 0.025. correct, or oh sorry, it should be
0.1.
0.1.
0.1, sir.
0.1. Okay. Okay, let's so that is how you should compute 0.1. Okay, so this is related to conditional PMF. Okay, let us go to the other problem. Other kind of problem you can see. What is the probability that he or she got S grade or is from less than 20 age group or both? So now what does this statement, how should I convert, or what all the values I should be including in my probability?
Okay.
So think about it.
Not grade is
Marginal of
equal to
grades,
or
Sir, we should take, I guess, the marginality of S grade plus marginality of less than 20 plus both. If they are asking, then means 0.05.
union.
Probability.
Okay, is it this? Everyone agreeing to this probability
No,
that
sir. Is it
This
joint
because
PMF
this union
of
type.
S and less than 20?
Less
Sir,
than equal
but
to.
we shouldn't add that
do
again,
I have-
because already
correct.
it is included within those two marginals.
Okay, let's discuss about this. I will give you three options. Just let me see how many of you choose the correct option. So the first option is, let me write it here only. So the first option I'm giving is probability that grades is S plus probability that this age random variable take is less than 20 plus probability that grades is equals to S and age less than 20. So this is one option. The second option is probability that grades is equals to S plus probability that age is equals to less than 20. So is equals to means, see, I am not defining, actually you should give random variables. So you should treat like 0, this 1, this is 2, and this you can take 0, this 1, and this is 2. Like that you can take, but I'm just writing it up. Or this, or the third option is, where should I write my third? Okay, maybe I will write it here. Probability that grades are S plus probability that the age is less than 20 minus this.
Yes, sir. Third option. Third option.
So the third option.
Sir, option C.
Option C.
Option C.
Yeah. Because in that earlier one, I was adding it 3 times. It was wrong. Yeah.
Right. So the third option should be the correct, because we are asking either he or she should have got S grade. So S grade, when I say S grade, all of these fractions come under S grade, or is from the age group less than 20. So age group less than 20, these fraction will come. So while I am computing the probability that grades being S, this is being added once. While I am looking for age less than 20, also I am adding this 0.05 second time. So what we mean is either she should have got S grade, or he or she should have got less than 20.
Is it like a union?
Union. Sorry, it's like a union. So the intersection part will come twice. So you have to subtract that intersection part once. Then you will get the correct probability. So the values from the joint PMF table. So you don't need to go with the formula or anything. From the joint PMF table, identify what all entries should I add. That's it. So you just have to add. So this 0.01 comes in the bin of grades S. So you have to add this. So this comes in the grade of S only. This comes in both. 0.05 comes in both. So I have to add this also. This 0.15 comes in the age less than 20. I have to add that. And 0.16 come in the age less than 20. So and the remaining 4 will not come in our any of the possible case. So they neither got S grade nor from the less than 20 age group. Okay, so you can also do that. 1 minus of, you just subtract these things, you will get the same value. So if you add that, what is the answer?
0.42.
0.42. 0.42. So this is actually from the joint PMF table. You have to understand what all values you want, what all the probabilities you have to include. So the final or fourth problem.
Sir, please repeat.
Sir, 1 second, sir. See this question: what is the probability that he or she gets S grade and from the age group less than 20
No,
or both?
It is not
What is
end.
both?
It is not end. It is or
Then,
is from the less than 20 age group.
Okay. Or is from less than 20 or both?
Or both means it's like getting S grade as well as from the less than 20 age group.
Okay.
So this is both case. So this is both case, and this is only S case. This is only less than 20 age case.
Okay.
So all these three things you should add from the joint PMF table. So the last problem is, what is the probability that he or she is neither got B grade nor is from the age group greater than 60 years. So the selected student is neither got B grade nor she is from the age group of greater than 60.
First 4 entries, sir.
Sir, we have 4 entries.
First 4 entries.
First 4, you mean? I hope these 4.
Yes.
Sir, by
4
complement we
entries
can also.
from SAN.
Yeah, correct. See, this has two ways to do. Either you compute the probabilities that the selected student is from B grade or from the age group greater than 60, and subtract this probability from 1. Okay, because they shouldn't come from here. So what you can do is 1 minus, they are coming from these sets. So 1 minus, either the student is from B grade, got B grade, or from the age group greater than 60. 1 minus of that you can do, or you have to identify simply. So it should identify the cells which are neither B grade nor from the age group greater than 60. So for that, anyway, you need to identify which are greater than 60 age group and the grades B. So grade B column is this, and I don't want this. Age greater than 60 is this. Even this also I don't want. So the so whatever I want is whichever not in the green circle. So I have to add up all these 4 values. So all these 4 values are neither B grade nor from greater than 60 age group. Okay. So 1 minus of these values you can do, or you can simply add these 4 values and you will get the answer as
0.45.
0.45. So you see, within one joint PMF table given to us, we can actually compute the marginal PMFs, conditional PMFs. Within the joint PMFs only, if the context is something different, then also you can you have to identify within the joint PMF what all cells you have to consider and add up the probabilities. Okay, so this is how you should solve the problem. Yeah.
Yeah, sir. In previous question, why are you subtracting the last one, sir? Can you please explain it again?
So why am I subtracting is when I am computing probability that grades is yes. Okay, when I compute probability that grades takes yes, it's like marginal of yes. So I'm adding 0.05, 0.05, 0.01, right?
Okay.
That will become 0.11. So this probability will become 0.11, and identify this particular 0.05 is already added to this, right? 0.11. Within this 0.11, this 0.05 is there, correct?
Okay.
The next thing, probability that age is less than 20. So age less than 20 is like again marginal I have to compute. of the row 1, right? When I compute, what I will get? 0.05 plus 0.15 plus 0.16. So it's like 0.31, 0.36, right? In this 0.36, I am again counting this 0.05.
Yes.
Right? This particular cell is counted twice.
Okay.
Right? But I shouldn't count it twice, right?
Okay.
This is like S. This is like both. The grade is S as well as the age group is less than 20.
Yeah.
Correct? But it is enough to count it once, but not twice, right? Twice it will increase the probability.
Yes.
So that is why I have to subtract that 0.05 once.
Okay.
So that is why.
So actually, union is actually either this or that, right?
Union is actually either this or that. If you know,
but then in this question, if you're given this or that or both,
right? I shouldn't have added both, but for better clarity, I just added both.
So the question, if it had been S grade or from less than age group, then we can subtract that part.
No,
which
right?
said. But both give, is confusing. Whether it is an intersection or what it is. Like union, in union you anyway subtract the intersection portion. Because A union B is A, probability of A plus probability of B minus probability of A intersection B. So, but this question, in this question, S grade or from less than 20 age group is anyway union, right?
Achha, is it the case? Okay, maybe I'll just remove all both. So last time what I got is I didn't have both, but last time someone said why not you put just or both for better clarity. That is why I have put that or. If you are confusing with that or both, I'll just remove it.
No, sir, but what you have written is correct, right?
Yeah.
0.45 is correct.
Yeah. Whatever 0.42 is correct.
Yes.
This is correct. Okay. So that is about the joint PMF, marginal PMF, conditional PMF. The main points I wanted to cover is these properties of joint PMF. This for sure you shouldn't forget. Okay. So these two properties you shouldn't forget for the joint PMF table. So these properties will help us if there are any variables given in the joint PMF. So for computing those variables, this joint PMF table, these properties will be helpful. And then you should know, once the joint PMF table is given to you, you should know how to compute the marginal PMFs. So table given to you, you should know how to compute the marginals. And sometimes marginals will also be given, but there will be some gaps in the joint PMF table that you have to know the connection between the marginal and the joint. If you know that, you can compute. Then the next point is how you can compute the conditional PMF. So conditional PMF can be computed using the joint and the marginal. So joint divided by marginal, I can compute the conditional. And this connection between joint, marginal and conditional will help you to compute the conditional probabilities. Given joint and marginal, you can compute the conditional probabilities using this property. And sometimes this property will be useful in the cases when you are unable to compute the joint directly. If you know the marginal and conditional, use this formula and you can get the joint PMF table. So that is there. And this is what, see, if we have given some context inside it, what you have to do is firstly convert, or whatever the English statements given to you, try to convert that into the statistical terms or mathematical expressions. So that is the difficult part. So you should work on that. So whatever, what is the probability that he or she got an A grade, we can directly ask something like, we can directly give you random variable x, y, 0, 1, 2, 0, 1, 2. We can directly ask what is the probability that x is equals to 0. So instead of asking it in that way, we will just include some context like this. So these are the real scenarios where you will be seeing. So in the real context, you should understand how you should apply statistics or how you should compute. So that is why the main part is converting these English statements into the mathematical expressions. Okay. So if you can work on this, then quiz 1 you no need to worry about week 1 and 2.
Sir, one small doubt. in this option number 2, when we were calculating the conditional PMF, we divided it by 0.5. That is the total marginal PMF. Why aren't we doing it for option number 3 and 4?
We are not dividing, right?
Yeah, why we are not dividing? For that also we should divide, no, sir?
That is not conditional, no?
Okay.
That is what you have to understand. What is conditional? What is the condition? What is the probability? So here we are not given any condition.
Okay.
So if you read it carefully, here the selected student is from 20 to 60 age group. We have given that.
Okay.
So there the condition, that is the condition given to us. But 3 and 4 we didn't give any condition. We are directly asking the probabilities.
Okay, sir.
Okay.
Thank you.
So let's move now. Go to.
Sir, there was a question asked by Purnendu. Practice assignment. Yeah, question number 9, I believe. Practice assignment 1, question number 9.
Oh, okay. Let's do that thing also. Okay. So let me open my friend. Just 2 minutes. Maybe you people can take break for some 2-3 minutes. Let me open my portal. Question number
9, sir.
9.
Is it suppose you flip a fair coin?
Yes, I think.
If a coin lands heads, you roll a fair 6-sided die sometimes. How many times you got?
50 times, sir.
Okay, 50 times. Okay, if the coin lands tails, you roll the die 51 times. Right? Let x be 1 if the coin lands head and 0 if the coin lands tail. Okay, let's do this. We have something like this. So this is PA 1.1 PA1 question 9. Okay. So what it says is, so I have there is an experiment, coin toss experiment. So once the coin is tossed, so coin toss is like either it can give me head or tail. So I am defining a random variable x such that it takes 0 if it lands tails and 1 if it lands heads. So this is what it is given. So write down what is given first of all. Then if the coin lands heads, so what that does mean, if the coin lands head means if the random variable x takes value 1.
Takes the value 1.
Okay, this is the condition. Now it is a condition. Okay, so if it lands 1, that means if you toss the coin and observe the outcome, if it is head, so till there you went. So that means this has already happened and we are conditioning on this. And condition, what you are doing is you are rolling a fair 6-sided die 50 times. Okay, so roll a die 50 times. So given that x is 1. The second thing what might have happened is x is 0, then what you have to do? You have to do roll a die
51 times.
So instead of writing roll a die 51 times or 50 times, I will define a random variable y, which gives me the outcomes. Y be the, okay, anyway they defined, let y be the total number of times you get the number 5. So they said y is defined as total number of fives we observed. Okay, So this is given to. This is the random variable. This is how I defined my random variable. So now you can see y given if it is x is equals to 1. Okay, this is the conditional distribution. So I will try to look at the distribution of y given x is equals to 1.
Okay.
So if I look it like this, this I know this will follow. So when x is equals to 1, I am rolling a die 50 times and the total number of 5s out of 50 times rolled. So that is how the distribution, right?
Okay.
That is what the distribution of y given x is equals to 1 means. Correct?
So what is that last word? Total number of 5s?
We observed.
Observed.
We observed in x tosses maybe. Okay. Some n tosses.
Sir, does it follow binomial?
It follows Bernoulli, right? You are looking at either 5 or not.
But we roll it 50.
We roll it for 50. That will follow binomial, correct?
So that.
So this requires some IID concept also. So if you
Sir, but the given question is x equal to 1, given y is equal to 10.
I didn't go there at all.
Okay, fine.
Okay. So that we need anyway. The final we need is probability that x is equals to 1 given y is equals to 10. Okay. So for that, first of all, you need to understand what all distributions we can understand. So first and foremost is x distribution. I know x follows Bernoulli half. Right? It's a fair coin, so it's Bernoulli half. Now you should understand we cannot directly understand y because I don't know how many times I rolled a die. Right? Either I will roll 50 times or 51 times. I don't know that fixed. Right? That is dependent on another random variable which is x. Right? Y is dependent on another random variable x. Correct?
Yes.
So if it is like that, so as it is dependent on another random variable x, you condition on x and look at the distribution of y. Then try are you able to get the distribution or not. So if I condition on x, when I say x is taking value 1, now I know that I will roll the die 50 times and I am looking at the total number of 5s. Correct? This will follow something like binomial
50 comma 1
binomial 50 comma 1 by 2. 1 by 6.
1 by 6. No,
so 1 by 6.
1 by 6. Because we have either one can be possible, 2, 3, 4, 5, 6. So getting 5 has probability 1 by 6. So probability of success is 1 by 6 here. So if you are unable to get the distribution of y directly, try to condition some random variable x, and look at the distribution. Similarly, I can look at the distribution of y given x is equals to 0. And this will follow binomial
51 comma
1 by 6.
So, quick question on this. So if I have to solve this now, for instance, say x is a random variable which is either 1 or 0 based on the toss, and y is right. So if I have to solve this, I need to calculate. So if I have to solve the probability of say x number of tosses, x number of total number of 5, say. For instance, if y is a random variable which takes the total number of 5s, okay. So if I have to solve this, how would I solve this?
You want the distribution of y, right?
Yeah. So y can take values from 1 to 100, 1 to 50, right?
1 to 50 or 51, right? You don't
0
know.
to
0 to 51, right?
0 to 50.
0 to 51. Okay. Okay. We are calculating the entire probability distribution. All right.
Distribution. Okay. So I can't directly compute the distribution because I don't know how many times I should roll a die. Either it is 50 or 51, and it is depending on x.
So if I slightly change this problem and say if I have to calculate say y being what is the probability that the random variable y takes the value, for instance, 2, then I have to do 1 by 2 into binomial 50, 2, 50, like the probability that the x okay, let me do it again.
Okay.
So if the random variable y is supposed to take a value 5, and I have to calculate the probability that y takes value 5, then on the numerator I have to calculate the probability of x being 1 and y being equal to 5 divided by x being 1, right? Is that correct?
In that case, it will become marginal, I think.
No, it's conditional, not marginal.
So you wanted probability that y takes 5.
Y takes any arbitrary value, say 5.
5.
So given x is equal to 1.
Given x is equals to 1, then it is like y is equals to 5, x equals to 1, divided by probability that x is equals to 1.
Got it, sir. Got it. Okay. Right. And if I remove that conditional probability, then I have to calculate for both. Like in case if x is equal to 1 and y equal to 5, or x equal to 0 and y equal to 5, right?
If you remove the condition.
Yeah.
If you remove the condition, that is what we are going to see. So I am trying to get the distribution of y here.
Okay.
Because I can't directly get, I look at the conditional and I multiply it by marginal so that I will get the joint, and from using joint I will get the marginal of y. So that's the big process we are going to follow. Okay. So this is the property I am going to use, f of xy, f of x of x. I can write it as f of x given, y given x is equals to small x of y. This is equals to fy of y, fy x given y is equals to y of x. So what I am going to do is, I know this and I know this, right? I know this because I know the distribution of x, and I am looking at the conditional distributions, y given x is equals to something. So that means I know the conditional distribution. This is what I said. If you are unable to get the joint, what we do is we multiply marginal with the conditional, and after multiplying I will get the joint. So once you get the joint, I can get the marginal of fy of y. So from joint, as we discussed above, if I given joint, I can compute the marginal. So using joint, we will compute the marginal by summing up all x's. Okay, this is the method you have to follow here, because I can't directly come up with the distribution of y. Why? Because again, y is dependent on x outcome. So if x is 0, then y is behaving something different. If x is 1, y is behaving something different. So that is what we observed here. So that is how you should follow also. So right now, what all distributions I know is x distribution I know, and the conditional distribution y given x is equals to 1, x is equals to 0 I know. So after knowing these things, I will put it here and I will compute the margin. I will compute the joint. So that is what I can do. So I can compute fxy of 0, 1, or simply the product itself is the joint. So I can use that fx of 0 times fy of x is equals to 0 of y plus fx of 1 times fy of x is equals to 1 of y.
Okay. So what is the question asking for? Sorry, I missed it.
Fy of y.
Fy.
Okay. So how I got this? I got this from here. So if I wanted to compute fy of y, I should sum up all the unwanted. So I don't want x. X belongs to 0, 1. Fx of x times fy of x given x of y. So I have to actually sum up the joint distribution. The joint distribution, I can write it as product of marginal into the conditional, where my x takes either 0 or 1. I have to sum up it. So when it takes 0, this is the term. When it takes 1, this will be the term. So I'll get the distribution of y. So once I get the distribution of y, the question asks probability that x is equals to 1 given y is equals to 10. So they are asking probability that x is equals to 1 given y is equals to 10. So this is actually f(x) given y is equals to 10 of 1. So this is basically they are asking for this. And again, if you know this, and we know this, it is just simply you divide this particular term with fy of 1. So that is what we are going to do. So this is basically probability that x is equals to 1 comma y is equals to 10 divided by probability that y is equals to 10. So this joint, we will write it as product of marginal into conditional. So something like this, fx of 1 into fy given x is equals to 1 of 10 divided by probability that y is equals to 10 is basically fy of 10. So it is, you just have to substitute instead of small y, you just have to substitute 10 and complete. Okay, so that is why I said this particular connection is very important. The joint, writing the joint as product of marginals. So one way you can write marginal of x into the conditional. In the other way, you can write it as marginal of y into the conditional.
That is the same as law of total probability.
Law of something like that. Law of total probability. Yeah. So you can always correlate with that probability axioms. Okay. So that is there. That is there. But you shouldn't expect the difficulty of questions in quizzes will be like this.
I mean, it would be more difficult or less difficult?
Less, I said. I mean less difficult.
Okay.
Okay. So let us just move and let me talk about the independence thing also. So when do we say two random variables are independent to each other? So we have seen the joint between them, and marginal PMFs we have computed, conditional PMFs we have seen. Now we will also see the independence between two random variables. So that means, is x dependent on y or y dependent on x? Okay, something like that. So what do we mean by independence is, if my random variable x is taking values, is that being an impact for the random variable y, or is it not impacting anything? So if I vary x, my random variable, the randomness of y is not differing much. Or in other words, simply the conditional PMF, so even if I condition on x, the distribution of y is acting same like as marginal, then I say, even though you condition on x, the distribution of y is not changing much. So whatever the distribution it has, individual distribution it has, the same conditional distribution it is having. So that is what independence means. So let me write down in a formal way. So independence between random variables. So suppose x and y are two discrete random variables, and with ranges again tx and ty, okay, and it has some joint PMF. So fxy is the joint PMF. So I say x and y are independent to each other if the joint can be written as product of marginals. Can be written as product of marginals for all T1 belongs to the range of X and T2 belongs to the range of Y. So what does this mean is, if I can split the joint as product of marginals, then X and Y are independent. And it should be true for all T1 coming from X and T2 coming from Y. So in other words, so instead of saying this, so this is basically says that joint PMF can be written as product of marginals. So instead of saying this, in other words, I can say, if I can write the conditional PMF if my conditional PMF is equal to the marginal PMF, so both ways, Fy of X, X of Y, Fy of Y, then for all, this is for again for all T1, T2, or for all X belongs to Tx, Y belongs to Ty. Okay. So if this is being hold true, then also we say X and Y are independent. So I proved this. Okay. Okay. So this is simply telling that conditional PMF is equals to marginal PMF. So even though you say conditional PMF equals to marginal PMF or joint PMF is actually product of marginals, both are same. Both are same. So if this is being true, X and Y are independent to each other. This is a formal way to define. But when a table is given to you, how do you simply identify what all things you should check for the independence case? So let me bring the same table. Maybe I just can't copy directly. Maybe I'll take a new example. So this is X, this is Y. Let X takes 0, 1, 2, and Y takes 0, 1, 2. So again, if we are asking for independence or any question, if there is any unknown value, unknown variable sitting inside your joint PMF table, you just have to use the property of joint PMF table. Sum of all entries should be equal to 1 and get the unknown.
Sir, sir, what is that you have written? Just can you just scroll up? Conditional PMF is equal to marginal PMF.
Yes.
That is in case of independence.
In case of independence. So this is the statement is starting from here. Okay, X and Y are independent to each other if this is true.
Okay.
So now let me take the values. So maybe okay, 1 by 6, 1 by 12, 1 by 12, 1 by 4, 1 by 8, 1 by 8, 1 by 12, 1 by 24, 1 by 24. Okay, so these are the joint PMF values we have. If I wanted to conclude whether this X is independent of Y or not, my first step is to find the marginals. So because I need to check for the condition that whether this joint PMF is being equal to the product of marginals or not. For that I need individual marginals. So in order to compute the marginals, what I have to do, if I have to compute the marginals of X, I have to add up all the column values. So if I add 1 by 6 plus 1 by 4 plus 1 by 12, I am going to get half. This will be 1 by 4 and this will be 1 by 4. Okay. So if I add if I want the marginals of Y, I should add up all the row values present in the rows.
1 by 3.
This will be 1 by 3,
1 by 2 and 1 by 6.
Now what I have to do is, I have to take each and every entry inside the table. So I have to start from this entry. So this is basically fxy of 0, 0. So this is 1/6. I have to check whether this fxy of 0, 0 is being equal to fx of 0 times fy of 0 or not. So for this I need fx of 0, which is half, fy of 0, which is 1/3. So if I look at the product, it is 1/6. So these two are equal. So for this particular entry, the independence is what? So similarly, you should check for this entry, 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 and this entry. So there are 9 entries. All the 9 entries should satisfy the property joint PMF is equal to the conditional PMF. Okay, that property should be satisfied, and then only you can conclude that random variable x is independent of y or y is independent of x. So is this?
So can I ask a quick question here? So here for independence, we have to check for all the 9 entries, right?
For independence, yeah. The point I wanted to make here is, just please be on mute. Do we really need to check all the 9? So for the condition purpose, we should check, and if you can check, it will hold true. Is it necessary to check all the entries, or is there any optimal solution for this? Is what you have to understand.
At least check 8 of them, so 9th one would be already.
Is it at least 8, or is it at least 7 or 6? So if you check 6, will other 3 work?
So we need to check all the entries. To disprove something, we should to disprove something, we can take one of them is not satisfying the condition, but for proving, you have to check all the things.
You have to check all the entries, is what you say, right? But that is not the optimal. See, for now, as our tables will be like 4 cross 3 or 3 cross 3, the entries are 9 or 10. That's it. Okay. So for that cases, you just check everything. But what if the table is very large, like 100 cross 100? Do you sit solving
the diagonals?
Not particularly, but there is some optimal solution for this, which if time permits, I will discuss that. Okay. But
in one of the sessions you had asked this question.
Yeah, I asked this question, right?
Yeah.
I didn't answer.
Yes.
I will just answer that if there is time. So I have to discuss IIDs also. So after discussing IIDs, we will just come back to this. But for independence, for as of now, just you have to check all the entries, and if all the entries are satisfying this property, which is joint PMF is becoming equal to the marginal, then we will conclude x and y are independent to each other or not. If not, they are not independent. So even if it fails for one case, like even if it is failing for this particular case, let's suppose say if it is failing for this particular case, here it is independent, but what I mean is, if for one particular case fxy of 1, 1 is not being equal to fx of 1 times fy of 1, then we straight away say that x and y are not independent. So even if it fails for one particular entry, then we will conclude that x and y are not independent. Okay. So in this case, it is very easy to observe. You can check for all the 9 entries. It will give us every entry can be written as the product of marginals. So this we can conclude that x and y are independent. Okay.
So are we going to discuss? I remember in the first lesson, I think sir discussed multiple distribution for more than 2.
Multiple random variables. This is just the extension of what 2 random variables is, right?
Okay.
So It's not.
It's okay.
I don't want to
discuss
discuss.
it.
Yeah.
I just wanted to once review that formula where they had used conditional distribution for that calculating.
Factorization, factoring.
Yeah. That's the one.
So factoring thing, huh? Okay. Maybe for conditional thing I will discuss. Okay. Okay. So that let us discuss the conditional distribution, conditional PMF for more than 2 random variables. Okay. For 2 random, let me write for 2 random variables first, so that we can connect these 2 random variables to multiple random variables. So conditional PMF we are discussing for more than 2 random variables. For 2 random variables, I will just write it down. So let's say x1 and x2 are 2 discrete random variables. So if I wanted to look at the conditional distribution of conditional distribution of x1 given x2 is equals to some t2 of t1. So how I can write this? So how I can write this conditional distribution? This will basically, you can write this as
Joined by margin.
Joined by margin, correct? So this is like fx1 x2 of t1 t2 divided by fx2 of t2. Or else I can write that joint, observe carefully, this joint I can write it as fx2 of t2 times, okay, fx1 of x2 is equals to t2, or I can write it, I can bring this term this side, the other term. So fx1 given x2 is equals to t2 of t2 times the conditional probability fx2 of t2. Okay. So if I extend this argument to multiple random variables, let me say fx1 to some xn, have some joint distribution fx1 xn, some joint distribution. How can I write this joint distribution? By factoring. So how do I factorize this? Factorize means writing it in terms of 2 products. How did I write this joint as the product of conditional into the margin, right? So here, before I have only 2 random variables, I conditioned on 1 random variable and I looked at the distribution of the other random variable. So similarly, can I do the same for this thing? So t1 to tn. So now this is nothing but, you see, probability that x1 takes t1, x2 takes t2, and so on, xn takes tn. So now look at how I am writing this. So x1 is equals to t1, and the rest of the thing I am looking collectively. x2 takes t2, it's the joint distribution of x2 to xn. Okay. So if it is like this, now again, this is one event and this is the another event, and I am looking at the joint between 2 things, two random variables. I can write this as the first random variable being conditioned. So I can write it like x2, x3. So this is the joint till xn, given x1 is equals to t1 of t2 to tn times f of x1 times t. So just like in place of x2 or in place of x2, we have the joint of x2 to xn. That's it. So split the n random variables into 1 random variable and n minus 1 random variables. N minus 1 random variables is a joint between them, and x1 is another random variable. So now you have 2 things, joint between 2 things. So you can write it as conditional conditional of one thing given the other thing times the marginal of the other thing, something like this. So once you can write this, now see this thing, this is the condition. Again I can write this as probability that x2 is equals to t1, t2 to xn is equals to tn divided by probability that x1 is equals to t1. Okay. Again in the wrong way.
Sir, x2 is equal to
x2 is equals to t2.
Joined by marginal, right? Condition is joined by marginal. So it is by.
Okay. Maybe I am going in the wrong direction. So instead of so the same thing I can write it like this also. So instead of writing in that way, I can write x1 conditioned on x2 to xn.
Sir, is it that, or is it like probability of x1 is equal to t1 into probability of x2 equal to t2 given x1 equal to t1, and is it that way?
Yeah. So this is the way. X2 is equals to, so I am taking this conditioning on this now. So I don't want to condition on x1. So let us condition on this. X2 is t2 to xn takes tn of t1 times fx2 to xn t2 to tn. Okay. So this is the conditional. So let's keep it aside. Now this has become the joint now. Again I can reduce this joint as, I can factorize this joint as product of marginal into conditional. So this is basically a probability that x2 is equals to t2 to probability that xn is equals to tn. And again now treat x2 as one random variable and the remaining x3 to xn as one collective thing, some joint thing. Now again,
sir, what are you doing?
Hmm?
Ultimately, what are you trying to do?
I am trying to factorize this fx1. So I have factorized this fx1 x2, right? This joint as product of marginal into conditional, right? So the same thing I am trying to do here. So how can I write this joint as product of marginals, product of conditionals and marginals? Okay. So again repeat the same process. X2 is equals to t2, x2 as separate and x3 to xn as separate, and I can write that as fx2 of x3 takes t3 to xn takes tn of t2 times, again you will get fx3 to xn of t3 to tn. So this term will be there, this term will be there, and multiplied by joint between x3 to xn. So again repeat the same process. Now if you write this, now treat x3 as some random variable and x4 to xn as the another joint random variable. Again split it into factorized. Again factorize it. Ultimately what you are going to get is, if you do that, fx1 to xn, t1 to tn, I can write this as fx1 given x2 is equals to t2 to xn is equals to tn of t1 times fx2 conditioned on x3 to xn t2 times fx3 conditioned on x4 to xn t3, and so on. For the last one you will be having fxn minus 1 given fxn is equals to tn minus 1, and lastly you will have fxn of t. Okay. So this is how you can factorize. But for quiz point of view, I don't think you need all this. Okay.
Okay.
Okay, let's move to another important discussion, which is independent identically distributed random variables. So when I talk about IIDs, it means if I have some random variables x1 to xn, let's say, they are said to be independent and identically distributed if all of them are independent to each other. So x1 is independent to x2, x3 to xn, x2 is independent to x3, x4 and xn. Any two random variables you pick, they should be independent. When I say independent, what does that mean? I can write the joint as product of marginals. Okay, always remember this. Not remember this, understand this. Whenever they are independent, you can write the joint as product of marginals. This holds true for multiple random variables also. So I didn't discuss that, but it is true for multiple random variables also. So when I say they are independent, that means their joint is equals to product of marginals. So independent identically distributed random variables must be independent is one point. And the next point is they are identically distributed. So identically distributed means the marginal PMFs are identical. So if I compute the marginal PMFs of x1, x2 to xn, all of them have identical distribution. Identical, you mean equal distribution. So that means fx1 of x1 is equals to fx2 of x2 is equals to fxn of xn. Something like this. So everything x1, x2, xn, instead of all that, you can simply say x. So fx1 of x is equals to fx2 of x is equals to fxn of x.
Sir, can we say that the probability of, say, random variable x1 taking value, say, 1 is going to be the same as x2 taking value 1 and xn taking value 1?
Correct. So what do we mean by this identical is all the random variable range of xi's are equal. Okay, range of x's are equal, and within that range values, the corresponding probabilities are also same. So when x1 is taking values 0, 1, 2, x2 will also take values 0, 1, 2, 0, 1, 2, all xn also will take 0, 1, 2. So, and if x1 is taking 0 with probability 1 by 4, 1 with probability half, and 2 with probability 1 by 4, then x2 also follows the same distribution. x3 also follows the same distribution, xn also follows the same distribution. And added to that, x1 is independent to x2, x2 is independent to x3, every two random variables are independent to each other. Then I can say x1 to xn are IID random variables. Okay, so I have examples below. So let me take an example and it will get clear. So now you see, when I say x1 to xn are IIDs coming from Bernoulli 1 by 3. What does this mean? So usually we denote these IIDs like this. So x1 to xn follows independent identically distribution of Bernoulli 1 by 3. What does this mean is the joint, the distribution between x1 to xn can be written as product of marginals like this, fx1 of t1, fx2 of t2 to fxn of t3. Added to that, x1 follows Bernoulli 1 by 3, x2 follows Bernoulli 1 by 3, xn follows Bernoulli 1 by 3. When I say that, then I know fx1 of x. This is simply fx1 of 0 is 2 by 3 and fx1 of 1 is 1 by 3. So similarly, when I say fx2 follows Bernoulli, I know fx2 of 0 is 2 by 3, fx2 of 1 is 1 by 3. You see every random variable x1, x2 to xn all have the same PMFs. So the PMF of x1 is same as PMF of x2. PMF of xn is also same as xn of 0 is 2 by 3. Fxn of 1 is 1 by 3. Okay, they have the same distribution. Once they have the same distribution, I can write the joint as, you see this fx1 of t1 is basically equal to fx2 of t2. So this fx1 of x times fx2 of x and so on fxn of x. I can simply, instead of writing fx2 of x, I can write fx1 of x only. Fxn of x can also be written as fx1 of x. So it is simply the product of fx1 of x times fx1 of x. Because they are equal, they are identical, I can replace x2 to xn as x1 only. Till fx1 of x. So this fx1 of x is n times. So we will be getting something like this, fx1 of x whole to the power n.
Sir, I have a quick doubt here. When we say a random variable is uniform random variable, it means it takes whatever values it takes, all of them have the same probability. Correct?
Not uniform.
Uniformly distributed. If a random variable is I'm talking about uniformly distributed random variable. Over there, the probability of all the values are same for that particular random variable. And this is slightly different where we say IIDs, where even though the random variable might not be uniformly distributed, but multiple random variables will have the same range, and probability of each values might not be the same within a random variable, but across it will be the same. Like
here the PMF is same, right?
PMF is same.
PMF is same. Okay, so x1 taking value 0 might not be the same as x1 taking value 1, but x1 taking value 0 is same as x2 taking value 0.
0, correct.
Okay.
Similarly, x3 taking value 0 and so on, xn taking value 0. Okay. All these values are equal. So they have identical PMFs. Identical PMFs, you can treat it as they have, if x1 is taking value 0 with probability 2 by 3, then all other random variables taking value 0 will have probability 2 by 3. Similarly, for every value in the range of x1, if it has some corresponding probabilities, for all x2 to xn random variables will also have the same probabilities. It may not be uniform. Okay. Similarly, I have one more example here. So let's try to understand this particular random variable. So x follows 0, 1, 2 with probability 1 by 3, 1 by 2, 1 by 6. Here my random variable x is not uniform. So that you have to observe that first. And now what I said is, suppose x1 to xn are IID samples with distribution x. What does this mean now? Understand this first. So what does this mean is fx. So first of all, x1 to xn are independent to each other. IID inside that says all this x1 to xn are independent to each other. This is there. And the next thing is identically distributed. The first I is basically independent to each other. The identically distributed means x1 follows 0, 1, 2 with probabilities 1 by 3, 1 by 2, 1 by 6. So this is the distribution of x1. Similarly, x2 also follows 0, 1, 2 with probabilities 1 by 3, 1 by 2, 1 by 6. Similarly, like this only and so on, xn will also follow 0, 1, 2 with probabilities 1 by 3, 1 by 2, 1 by 6. Now you see probability that x1 is equals to 0 is equals to probability that x2 is equals to 0 and so on, it is equals to probability that xn is equals to 0. Similarly, not only 0, probability that x1 is equals to 1 is equals to probability that x2 is equals to 1, x3 is equals to 1 and so on, xn is equals to 1. And the last one also, probability that x1 is equals to 2 will be equal to probability that x2 is equals to 2 and so on. So you see the PMFs of x1, PMF of x1. So this will be same as PMF of x2. That will be same as PMF of x3. So all the PMFs will be identical or equal. So instead of considering x2, x3, x4, xn, you can simply consider all other random variables as x1 only. Or you can either treat all x1 to xn as x itself. because every random variable x1 to xn is following the same distribution of x. So whatever the corresponding probabilities you compute between x1 to xn, the same you can replace it with x. So let's observe while we do this problem, we will get much more clarity on it. So what I want is find the probability that x1 not equals to 0, x2 not equals to 0, and so on, xn not equals to 0. So this is a joint distribution. Okay. So as we said that they are independent to each other, the first thing what I will use is that independence thing. So using that independence thing, I can split this joint into product of marginals. Okay. Once I split this into product of marginals, now I know the distribution of x1. Okay. What is the distribution of x1? This is the distribution of x1. And I can also compute the probability that x1 not equals to 0. So what will be the probability that x1 not equals to 0? This is
1 minus p of x equals 0.
P of x1 is equals to 0, and this is x1 is equals to 0, probability is 1 by 3. So 1 minus 1 by 3 is 2 by 3.
2 by 3.
Now observe, so this is 2 by 3 first thing. So is it necessary to go to x2 and again compute 1 minus probability that x2 is equals to 0? This thing. If you compute, what will you get?
So it would be the same.
2 by 3 is again the same.
It will be 2 by 3 only. And if I compute every other, even the probability that xn not equals to 0, I will be like probability that xn is equal 1 minus probability that xn is equals to 0. And even if you compute this, you will get 2 by 3. You will get the 2 by 3 only. So if you observe correctly, the probability that x1 not equals to 0 is same as probability that x2 not equals to 0, probability that x3 not equals to 0, and so on, probability that xn not equals to 0. So what I can do is, instead of x2, xn, x1s, I can simply, even if you see probability that x not equals to 0, you will get 2 by 3.
P not equal to 0 or to the power n.
Correct. So I can simply write this as x not equals to 0 into probability that x not equals to 0 into. So that is the liberty that we get from IID. So if I write it like this, now this will become probability that x not equals 0 to the power n. Okay. So you can directly say to the power n. Now this is equals to 2 by 3 power n. So even though you do sit on computing each and every probabilities, you will end up getting this. But using the property of identically distributed thing, we have independent and identical. For independent, we have reduced our joint to this product of marginals, and each of the marginal is identical. So what I made is, instead of taking all the n random variables, I collectively took it as one random variable to the power n. So you see how simple we made the joint to simply, if you know the distribution of x, you can compute the probability. So it just take the power. So the second problem is also like find the probability that one appears exactly once. What do we mean by one appearing exactly once?
So out of the n random variables, only one take value 1.
Yeah.
One is
one
taking
of them
value.
only take 1.
So what does this mean is probability that x1 not equals to 1, x2 not equals to 1, and so on, some xi is equals to 1, and so on, xn not equals to 1. So this xi can be from 1 to n. So this you can start from x1 itself. So it's like x1 is equals to 1, and everything else, rest of the things are not equals to 1. Plus. So it's not only x1 taking 1. x2 can also take 1, and the rest of the things will not take 1. So this is also there. Like this, there are n chances, right? x1 takes 1, x1 can take 1, x2 can take 1, x3 can take 1, x4 can take 1, like this. xn can take 1. But if you see, if you write down everything, it will get very longer. So what I can do is, you see, you observe this particular thing. So I can write this as simply probability that x1 is equals to 1 times probability that, so something like this, probability that x is equals to 1 times probability that x not equals to 1 to the power
n minus 1.
n
N minus 1.
n minus
1.
And this
whole
is
multiplied.
So this is
Whole
not only
multiplied by
this, whole multiplied by n, that will come. So for this it is this. If you try to compute for the second one, then also you will get the same thing. So probability that x is equals to 1. So for this x2 you are going to get probability that x is equals to 1. For the remaining n minus 1 you will get probability that x not equals to 1 to the power n minus 1. So like this, x3, x4, x5, xn. So you have to add n different probabilities, right? What happens is you will directly get n times this.
N into 1.
So this is like n into 1 by 3 into 2 by 3 power n minus 1.
Sir, it's kind of binomial distribution, isn't it?
Correct.
Yes, it's a binomial.
So it's like, so it will follow a binomial, and we are looking for equals to 1 case. Okay, that is like nc1 into 1 by 3 whole power 1, 2 by 3 whole power n. So something like this. So from this you can extend your argument. So if I ask like find the probability that 1 appears 3 times, so what might be the probability?
And choose 3
1
and then
minus
1 by 3
Correct.
raised to 3 and 2 by 3 raised to n minus 3.
Correct. So this is correct. And try thinking about this, why this is correct. And choose 3, 1 by 3 to the power 3 times 2 by 3 power n minus 3. Okay. So that is there. And yeah, so IIDs are very important. And then this geometric distribution, this is one small property, memoryless property we say. So when x follows geometric p, fx of k will be like 1 minus p whole power 6. So I'm getting the success at the kth time. So 1 k minus 1 times failures and followed by success. This is how the PMF of geometric distribution will be. And what this memoryless property states is, so if I wanted to compute the probability that x takes values greater than m plus n, given that x is greater than m, it is same as equals to computing probability that x is greater than. What it says is, so x starts from 1, right? X starts from 1, 2, 3, and so on m plus 1 to m plus n, something like this. So I know that x is greater than m. That means I didn't get the success till the m tosses. Maybe you see it in that perspective. So I have tossed for the first time, second time, third time, till the mth time I tossed, and all of them are failures. So now I am here at this particular point. So I know that till x is equals to m, I didn't get the success. X is definitely greater than m. I know this. Now, if I wanted to find the probability that x is greater than m plus n, so something like I won't get the success for m plus nth time also. What is the probability that x is greater than m plus n given x is greater than m? It is same as considering probability that x is greater than n. You can see now. So if you are at this position and whatever the information you have previously, all the failure information, you simply forget about it and you just start freshly. So whatever you have done here is waste of time kind of thing. Now you have to start fresh. So this is your first toss now. And you just have to look for, so if this is your first toss, this will be your nth toss. And what we want is, instead of looking at the probability that m plus n given x greater than m, you just start fresh considering that as the first toss. And you just simply look for probability that you are going to get your success after nth toss. So this will be like 1, 2, and this will be the nth toss. So something like this. So whatever you do till now, whatever the condition you have till now, is waste of. It's kind of waste. Whatever you did, it's kind of waste, and you just start freshly. So that is what it says. and even you can use this PMF, and you can get this. So write this conditional as joint divided by marginal. Some terms will cancel out and you will get. And I proved this in the previous lecture also. You can just go back and watch it. So this is one example I have. So if x follows geometric half, what is the probability that x greater than 8 given x greater than 5?
So it would be x greater than 3.
This is simply x greater than 3. So 8 you write it as m plus n. So this 5 is m. So once 5 is m, so n will be 3. That will be equal to probability that x greater than 3. So this is something like half power 3. Is this correct? It will
Yes,
be
sir.
3 of.
Yes, sir, it is.
Yes,
So
sir.
this will be 1 by 8. Or else you can compute it like 1 minus probability that x is equals to 1, minus probability that x is equals to 2, minus probability that x is equals to 3. So you can also do that. Okay, ultimately you will get 1 by 8. So that is how you can do, or else you just use the property of this. So you can do like this probability that x greater than 8 divided by probability that x greater than 5. Then write that probability 1 minus probability of start from 1 and subtract till x is equals to 8 divided by 1 minus probability that x is equals to 1, go till x is equals to 5. If you compute the big thing, you will end up getting 1 by 8. Okay, so that is the small thing. Okay, so function of next thing is function of a random variables. Function of a random variables, I don't want to discuss all the technical stuff. Let me take an example and let me talk about what is this function of a random variable mean. So basically, if you have random variables, we can also look at the functions of the random. Functions are like, if x is a random variable, functions are like 2 times of x, 3 times of x, x plus x square. So these are the functions, right? So the usual functions only. So we are not going to see x square and all. The main 3 things what we are going to see is sum of 2 random variables is a function, product of 2 random variables, minimum of 2 random variables, and maximum of 2 random. So these are the most important things. And to our exam point of view, mainly focus on this sum of 2 random variables and minimum of 2 random variables. Okay. So if I have given 2 random variables like this, x1, x2 follows IID Bernoulli 1 by 3. And if I have given you some function y, g of x1, x2, or simply even not this, if I can simply say some other random variable y, which is equals to x1 plus x2. What is the PMF of y? So very simple, very straightforward. So y is a function of x1 and x2. So you can use multiple methods. You can use a table method here in order to get the PMF of y. So you write down x1, you write down x2, you write down y. Okay, so x1 is 0, x1 can take 0, x2 can take 0. When x1, x2 takes 0, y takes 0. So similarly 0, 1, 1, 0, you write down all the possible cases. 1, 1. So this is 0, 1, the sum will be 1, 1, 0, the sum will be 1, 1, 1, the sum will be 2. And we have given their IID Bernoulli 1 by 3. So what does that mean? X1 follows Bernoulli 1 by 3, x2 follows Bernoulli 1 by 3, and x1 and x2 are independent to each other. So when they are independent to each other, fx1, x2, the joint will actually be the product of marginals. So it's simply like you take the probability of this times probability of this will give you the joint. So probability that x1 takes 0 is 2 by 3.
2 by 3 and 2 by
3 times 2 by 3, which is 4 by 9. The next one will be like x1 takes 0 is 2 by 3 times x2 takes 1 is 1 by 3 is 2 by 9. And now x1 takes 1 is 1 by 3 times x2 takes 0 is 2 by 3. This will be 2 by 9. And for the last case, x1 takes 1 is 1 by 3 and x2 takes 1 is 1 by 3. You just take the product of it, it will be 1 by 9. So these are the probabilities that y takes 0, 1, 2. So y takes, first of all, write down the range that in order to compute the PMF, you write down the range first. So this Ty is actually equals to 0, 1 and 2. So duplicates, you don't have to write it twice. So no need to write 1 twice. So it is enough writing 1 once. Okay, this is the range and its corresponding probabilities, you just have to get it from here. So for 0, it is 4 by 9. For 1, you have two rows. So 1 you are getting when x1 is 0 and x2 is 1. And 1 you can get from when x1 is 1 and x2 is 0. Okay. So 1 you can get it in 2 different cases, and each of the case have probability 2 by 9 and 2 by 9. Therefore, you have to add those probabilities. So this will become 2 by 9 plus 2 by 9, 4 by 9, and this will become 1 by 9. Okay. This is how you can do when you do it by writing the table. If you wanted to do using the joint PMF table, this is x1, this is x2, 0, 1, 0, 1. So you see, instead of writing from the joint PMF table, you write down the sum. So the entry values, you write the sum. So you write the y entry values are y values. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2. You see, this is 0, this is 1, and this is 2. So something like this it is coming. So for 0, you have to consider the case when x1 and x2 are being 0. For 1, you have to add up the cases 0, 1 and 1, 0. Okay, 0, 1 and 1, 0. And for 2, you have to consider 1 case. So this is very simple, small table. That is why we are getting only small, very simple 4 cases. If the table is large, then this particular way of solving is helpful. So if I say here itself, I am writing. So if I say x1 takes something like 2, 3, 4, and 2, 3, 4, something like this. Now writing it like this will help you much better. So you see now 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4, 1 plus 2 is 3, 4, 5. This will be 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8. Now if you see, this is 0, this is 1, this is 2, this is 3, something like diagonals. So you can see diagonally you have to consider all the cases, 6, 7 and 8. So if you want the PMF, this is what the PMF will be. So this will be this. If you add up all the probabilities in this line, that will give you the probability that y is equals to 0. If you add all the probabilities, that will give you the probability that y is equals to 1. If you add these probabilities, it will give you probability that y is equals to 2. For the sum, 3, probability that y is equals to 4, like this. So till probability that y is equals to 8. Okay. So
can I ask a question here? Since it was Bernoulli, that's why we can conclude that the values can be only 0 and 1. But in case if this particular question would have been on binomial, so how that question would be framed?
Question would be framed, huh?
How that would be framed?
Instead of Bernoulli, we will simply give binomial. That's okay. So binomial something 3 comma half.
Okay.
Then you have to write down the table, x1 and x2 separately and compute.
So the process would be the same, right? I mean, binomial 3 means, binomial 3 means 0, 1, 2, 3. IID means x1 would take the same value, x2 would take the same value, so it would be the same, right?
Correct.
But sir, it's actually I have. Okay, go ahead.
I mean, sir, it's actually binomial of 2, isn't it, sir? Like x1 plus x2. So it's the sum of Bernoulli's.
Sum of Bernoulli's?
I mean the y sum. Even if we calculate with that, we will get the same probability, like if n is 2 and...
Correct. So y follows binomial
2,
1 by 3. Correct.
Yeah, yes.
So, sir, I had the question regarding that actually. I mean, let's say, sir, it's given IID, right? So if it's not IID, let's say we have binomial x1 and x2. So, sir, if it's a generalized statement I'm making that if we add two binomial distributions, nothing defined, it would the sum. I mean, let's say x1 follows binomial, x2 follows binomial. If we add those, so the new variable is, I mean, random variable is x3. It would follow binomial as well. So, sir, until and unless it is IID, we cannot conclude that, right?
Correct. So
IID, it has to be IID.
It has to be IID if you are summing two binomials. If you want that that to follow a binomial, then it has to be IIDs.
So, sir, it should satisfy for any kind of distribution. Is it true? I mean, let's say it's not binomial. Let's say we have two Poisson distribution, x1 and x2, with let's say mean 2 and 3. So if we try to add those up, and they are not IID, so that new x3 or y, whatever the function would say, so it cannot follow Poisson until and unless those two are IID, right? So it
no need to be IID. No need to be IID for that. If you are adding two Poissons, it is sufficient to have independence case. So if they are independent, then the sum of two Poissons will become Poisson.
Okay, so in that case, only independent case should be the thing. The distribution could, I mean, the mean, if the means are different, that means distribution would be different as well. So, okay, so that's the case.
Yeah. So it depends on the distributions. Okay, few distributions will follow. If you add two distributions, getting the same distribution for Poisson cases, if you have just the independent condition, if you add two Poisson different lambdas, you will get the Poisson distribution only. But it may not be true for every other distribution.
Okay.
Sir, I think similar question is there in graded assignment also. It's related to men and women going to the mall, CT1 mall and CT2 mall. It's something like that. A similar question is there.
Okay, that depends on the last lecture. So maybe the sum of two independent Poissons, and if you see the conditional distribution of, if I say, okay, maybe I will write it down. So it is dependent on that particular things. So when we say x and y are okay, maybe x follows Poisson lambda 1 and y follows Poisson lambda 2. If I have condition that x and y are independent, just the independent thing, not the identically distributed, just the independent thing. So that means lambda 1 is not equals to lambda 2. I don't know whether lambda 1 is equals to lambda 2 or not. And if I look at z, which is x plus y, now I can say z follows Poisson lambda 1 plus lambda 2. This is proven, I guess, in the lecture. So you just go back to the lecture and
even sir, you proved it actually. I mean, in the in first couple of sessions or one
maybe
session.
Maybe we tried to prove, we have proved this. So that is there. And the other thing which is there is x given this z and y given this z. Okay. So if you see the distributions of these conditional distributions, it will turn out that this particular x given z also follows a known distribution, which is binomial distribution. N comma lambda 1
by lambda 1 plus lambda 2.
So something like this. And this will also follow binomial. So n comma lambda 2 by lambda 1 plus lambda 2. So.
Yes,
sir, again, I mean, for the probability, the logic is that total by my, I mean, no, not total by, I mean, favorable by total when we calculate the probabilities for this given part, right? And sir, n can be any value. I mean, x plus y, it depends on that. I mean, n can be any value.
N can
maximum
be
or something.
So something like this. N should be given. Maybe given. Okay. So these are few properties which we deduced after a series of solving and series of spending time on that. We have come up with this interesting things. Okay, and this may not be true for every other distributions and all. So these are special cases kind of thing. So Poisson binomial has some connection between them. This is the connection. So to condition one Poisson on another Poisson, it will turn up turn up that we will get binomial, something like this. And binomial and Poisson are interrelated. These things it is not good to discuss now. Maybe after quiz we can have some good discussion about this, some extended discussion of what we have to study for example. Okay. So that is there. So whatever the important topics I have discussed, follow these things, whatever we discussed today, solve more problems on these things. Okay. That is sufficient for week 1 and 2. Week 1 and 2 mostly focus on this marginal. So how to solve these kind of problems. When a joint PMF table is given to us, how to compute marginals, conditionals and all. And if there are any unknown constants, how to find that constants. And what else? Yeah. So when a function is given to you, something like sum of two random variables or product of two random variables, then if you know the distribution of the random variables x1 and x2, can you get the distribution of the newly defined random variable? So the function of random variable using the table method.
Hello.
Yeah.
Given one value of x, calculate the value of p of y given x is equals to something. So that is conditional only, no?
Yeah, right. That is conditional. Okay. So these are the main important topics which I wanted to discuss for today. Yeah.
If possible, please share the PDF also.
I will share the PDF. We will share the PDF. And one last thing I just wanted to close with is, maybe this will save your time in exam. So that independence case only. For two random variable case. So others, if you are having any other thing, I'm done. You can leave. So those who wanted to see how many entries you should check for a particular random how many entries in a joint PMF table you have to check in order to conclude the independence thing. So let me show you for four entries, like 2 cross 2 table. So if x and y are coming from Bernoulli, some Bernoulli. Let me not say IIDs also. Some coming from x is coming from some Bernoulli P1, and y is coming from Bernoulli P2. Okay. So this is x, this is y. This takes 0, 1, 0, 1. So this is, as I said, that is P1. This will be like 1 minus P1. This is P1. This is P2, 1 minus P2. Okay. So how many entries do I have to check basically? So how many entries are sufficient to check? Somebody in the previous discussion also many said that we have to check 4, we have to check 3, we have to check 2, we have to check 1. Did I give the answer for this?
No, sir. You said you would say it later. Later means later in that session, but we had some other discussion on it.
So the surprising or interesting thing about this is it is sufficient to check one. Yeah, it might be surprising to you, but If one entry satisfies the independence case, rest all three follows. Okay, so let me, if you
Is it true for any value n?
Huh?
Is it true for any value n?
Is it true for?
Is it true for any
value
n?
n? Any value of n.
Any value of n. Is it true for any value of n?
No. What I
So
mean
which means
is,
if it is more than 2 by 2, sir.
so if it's n by n,
Range,
in that case,
no. It's not n by n thing. I am just talking about 2 cross 2.
So can we generalize, sir? See, if it is 2 cross 2, it is 1. So if it is n cross n, then it is n minus 1.
It's not n minus 1 also. It is 2 cross 2 1. You maybe this is again surprising to you. For n cross n, it is n log n. So which is the optimal case. Okay, don't worry about that thing. So I don't want to talk about that. So that is the optimal solution. Okay, so optimization nowadays has become a huge thing, right? Everyone trying to optimize stuff. So for this, even if it is true for 1, so let's without loss of generality, I'm stating that this is true for 0 0 case. So if it is true, that means this is actually P2 times 1 minus P1. Okay. If it is happened to be P2 times 1 minus P1, actually what happens, you see now, if you know this entry value, you can fill all the 3 other entries using the marginals, right?
Yes, sir. By
So
subtracting with each of the marginals.
what will be this entry? 1 0 entry. This is simply P2 minus P2 times 1 minus P1. Right? What will turn out? If you simplify this, what will this be?
P1 only. P2 P1.
So,
P1 P2.
P1 P2. So you just simply see P2 minus P2. P2 and P2 will get cancelled. Minus P2 times minus P1, it will be P1 times P2. So this will be P1 times P2, which satisfies the independence condition. So similarly, if I see here, this entry, what will this entry be? This is like 1 minus P1 minus P2 times 1 minus P1. So if I take 1 minus P1 common, I'm going to get 1 minus P1 of 1 minus P2. Correct? Yes, no?
Yes.
Even this.
Can you repeat this part, the last one, which you did?
This one is like, in order to get this entry, I have to subtract this from this. Right? So 1 minus P1 minus P2 times 1 minus P1. So if I take 1 minus P1 common, I'll get 1 minus P2. And the last case, you see, either you subtract P1 minus P1 P2, or you subtract 1 minus P2 from this. Both will give you the same answer, which will give us P1 minus P1 P2. So I'm doing P1 minus P1 P2. This you are going to get P1 of 1 minus P2, which again satisfies the independence condition. So automatically it fills these values. So if the values are not this, then that is not a proper joint PMF table. Okay. So if I take any random example, instead of P1 P2, y 0 and 1. So you see, if we will simply take the first is satisfying. Let me take it as this is 1 by 3 and this is 1 by 4. Okay, let us take this is the product is 1 by 12. So this is being satisfied. So from this 1 by 3, this should be 2 by 3, because x is taking only values 0 and 1. If the probability that x takes 0, the probability that x takes 1 is 2 by 3 anyway. Similarly, the probability that y takes 1 will be 3 by 4. Okay. Now, once this is 1 by 2 and this is 1 by 3, this should definitely be 1 by 3 minus 1 by 12. No other value should be in that joint. Then this won't be 1 by 3. Then the first product will not be 1 by 12. So think it in that way. So this is 1 by 3 minus 1 by 12, and this is like 4, 3 by 12, 1 by 4.
3 by 12. Or
1 by 4. And this 1 by 4 is nothing but product of 1 by 3 times 3 by 4. So it will automatically fill. If you claim that these three are satisfying and this is not satisfying, then the value is wrong. Whatever the value given in the table is wrong. So definitely it will satisfy. Again here 1 by 4 minus 1 by 12, you will get 1 by 6. And here you will get 1 by 2. Okay, you can check.
Sir, one question on this. Sir, the value is wrong. That means either the sum of the, all the 4 entries won't be 1, or it won't be 1, or would be greater than 1 in such cases when you are saying that when 3 entries are matching but the last is not matching.
Last should definitely match. It won't form a joint PMF table. Maybe the sum of entries will not be equal to 1.
No, sir. No, sir. That's not what I'm trying to ask. I'm trying to ask, let's say we have 4 joint PMF table, and we have to check which one is let's say X and Y are there. So if X and Y are independent, then which table would satisfy? In such cases, so we have to check all the cases, right?
No, not
in
necessary.
Such cases, I'm saying.
In such cases also not necessary. That is what I proved, right?
Yeah,
so only the first.
Absolutely.
So
okay,
we need to check only the first cell, is it?
If it is 2 cross 2,
If it is a valid PMF.
If it is a valid joint PMF table, if first entry is satisfying the independence condition, definitely the other 3 will follow. Other 3 will follow. And it may not be the first entry. Even you check for the last entry also, this entry also, if it is satisfying, then the rest 3 will follow. Will definitely follow.
So sir, the only condition is given it is a valid PMF, only checking one entry is enough to check it is independent.
Enough. For independent for 2 cross 2.
That is only for 2 cross 2.
Only for 2 cross 2. Okay. Don't be like बाद में exam देने के बाद, don't be like I just checked only one entry for a 2 cross 3 cross 3 table, and you only said me that it is enough to check one. Special mention only for 2.
It is also possible that in the question the first entry might match, but the remaining entries might not add up to 1, right? So we'll have to check that also.
So that's what we are saying. It has to be a valid PMF.
Valid joint PMF table.
Okay.
Sir, what is the generalized case for this? Say
I already told, right? But
n log n.
N log n. You just have to compute.
If it's 3 by 3, we have to calculate 3 log 3, right?
3 log 3 number of so not even 3 log, like floor of n log n.
Okay. So in case of 3 log 3, it should be around something 3 or 4.
So you have to check 4 cases. It's not 3 or 4. You have to check 4 cases for 3 cross 3.
And that's base is 2, right? 3 log 3. So the log base is 2, correct?
Log base 10, right?
Okay, 10. All right. Okay.
So x, y. So I have to check whether it is log base 2 or log base 10.
Okay.
It is log. Usually log we will take base 10.
Okay.
If it is 3 cross 3, then you have to check these 4. If these 4 are satisfying, then definitely these things will follow.
Any 4, no sir?
Any 4, not only these 4, any 4.
And I doubt in the exam we might get more than 3 cross 3.
If you get more than 3 cross 3, then it's all for everything. Okay. So this is just for added knowledge. Okay, this is not even taught in the lectures, or nor you will find these kind of topics discussed in any of the textbooks. These are after again series of spending time on this joint PMF tables. Scientists, maybe very few identified this. Even I tried to come up with this. Initially I thought something like n minus, for an n cross n, I thought it would be n minus 1 times n minus 1. So it's like smaller square, n minus 1 whole square. Like it looks valid for
You
at least
said
2
n
cross
log n,
2.
right?
I said n log n, but what I proved is n minus 1 whole square. N minus 1 whole square is not a good bound. It is not better. Optimal is n log n. But at least for your case, I can give you damn sure that you just check for n minus 1 squares. For 3 cross 3 and 2 cross 2, it will satisfy. For 3 cross 3, you need to check 4 entries. For 2 cross 2, you need to check 1 entry. Stating that, all the best for your exam. Maybe next week I won't be available.
So what about revision for week 3 and 4?
Week 3 and 4, it's on Tuesday, okay?
Okay.
So, yeah, mentioning that this is my last session before quiz 1. So, do well in the quiz 1. I will meet you after quiz.
Anything would
Thank
you
you,
like
sir.
to add?
Thank you.
I mean, for quiz, I mean, how should we prepare or something? I mean, last moment, anything if you want to add.
Solve all the questions correctly.
So don't be nervous.
that-
Okay. Only one suggestion I can give is don't sit on one particular question and waste time. Do not waste time. Basically. So if you are unable to get the problem within by 5 minutes or such, just search for easy problems first of all. So I suggest waste 2 or 3 minutes to glance each and every problem first, to identify what all easy questions are there in the paper. So it's like getting cashews in upma. So there will be some cashews. So you just have to search for the easy problems first. Okay, search for that, solve them quickly, get the passing criteria, then go for the difficult questions. Do not sit on difficult questions and try waste. Do not waste time. And also you might see 1 or 2 difficult questions in the paper. Do not worry about the difficulty level also. If you follow activity questions, practice and graded assignments, if you are thorough with your basics, then definitely you will do good.
So we have a previous year question solving by TAs also, right?
That is there, I guess. So do attend these revision sessions. This will definitely help you. So these revision sessions are slightly inclined towards your quiz preparation. Okay. So whatever we discuss in the revision sessions, so that are very useful topics. So focus more on those.
Sir, are those previous year question papers available somewhere on the portal?
Not on the portal, man. Definitely we won't be providing, but there are many student communities already sharing previous year.
Okay.
Just get it done. Okay. Okay. Okay, then have a good day and all.